How's everyone doing today? Doing good. That's good. Did everyone get is everyone able to see their grades, I'm assuming, for the midterm? It should have been posted. Excellent. 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 Alrighty. Let's go ahead and get started. Okay. So today we're going to look at tangent planes to graphs of functions of two variables, and also linear approximation, and also a bit of differentials. And all of these are essentially going to be the same. There's going to be like one formula that we're going to be using the whole time, basically. Okay. So as always, I like to go back to the case for functions of one variable, which is usually simpler, and we usually have already learned it, and show how it's similar to the case of the function for more than one variable. So suppose we have the graph of a function f of x of one variable. So this is this is the graph of a function f of x. So it's a curve, right? It's y equals f of x is that curve. And suppose we look at a point x equals a. Right here. So on the graph corresponds to the point a f of a, and we can look at the tangent line to the curve at the point a f of a. So this is the tangent line. We'll call that L of x. So what do we know about the tangent line? What's the slope of our line?
The derivative?
It's the derivative of f at a. So we know the slope is f prime of a, and we know it goes through the point AF of a. So we can use point slope form. So this is, let me write it this way. This is the line y equals f of a plus the slope f prime of a times x minus a. That's the equation of the line, the tangent line. So what is important about the tangent line? Well, it's really simple. the equation of this is linear, right? It's a really simple function, whereas the function itself could be very complicated. Linear functions are nice when you're trying to approximate something. Really easy to use to approximate. And if you are, so what the tangent line is the best linear approximation of your function near the point A. So if we zoom in there, so there's our function. Here's a tangent line. If we zoom in more and more, the tangent line and the function itself and the graph of the function become almost indistinguishable. They basically, well, pretend they approach each other. So that means if you're really close to A, if your x value is really close to A, the value when you plug in that value of x on the graph of your function, the y value, so the value of the function is really close to the value on the line if your x value is really close to A. So if we want to approximate our function, we can plug it into our linearization of f. And it's a really, really simple function. Oops, sorry, that's supposed to say linearization of f at A. Really easy to calculate an approximation by hand using that. Okay. So the case for functions of two variables is similar, except the graph for a function of two variables is now a surface. So this is our surface z equals f of x, y. And if you pick a point P on our surface, we can look at the tangent plane to the surface at the point. So tangent plane to the graph. So suppose this is the point P. So the graph of f at a point P, well, let's just call it AB. So at a point A, B, f of AB. And then the same things hold true. It's the best linear approximation when we write the equation of the tangent plane. It's going to be the best linear approximation of our function at the point. So if you're really close to AB, if your xy value is really close to AB, you can use the equation of the tangent plane to approximate your function there. And also the same thing holds true. If you zoom into your graph at the point AB, the tangent plane and the graph of the function become indistinguishable. They get closer and closer and closer together. Well, that's true for nice functions, but we really are mostly just going to be dealing with only nice functions in this class. And they have a whole section on what that means at the beginning of 14.4. Has to do with differentiability and that kind of thing, but we're not going to concern ourselves too much with that. Okay, so let's derive the equation of the tangent plane really quickly. And I am going to use the drawings in the book to explain what's going on so I don't have to do that myself. It'll be much easier to see what's actually going on in here. Okay. Okay. Oh, bro. Oh, you love to see it. You love to see it, guys. Okay. Achieve is awesome. Just like stopped responding on me. Very cool. Very cool. Zoom. Ha! Okay, that doesn't help. Okay. Or you could do that again. Okay, whatever. We'll take it. Okay. So all right. So so what we're going to do is we're going to find a couple vectors which are parallel to our tangent plane. Oh my God, please stop. Okay, you know what? And then take the cross product to find a normal and derive the equation of the tangent plane really quickly. Okay. Guess I'm not trying to close the sidebar. Okay, so here's our tangent plane. All right, so if we look at the curves, so if we look at this picture here, basically if you fix y equals b, so we're at the point AB. I hope everyone can see this. So we're at the point AB. If we fix y equals b and look at the trace on our plane, that gives a curve, right? And it turns out, so the tangent to that curve at the point AB is going to be parallel to our plane, which you can look in there further if you want to convince yourself that's true. And it turns out that the slope of that guy is in fact the partial of f with respect to x. So if we look at the tangent line at that point, it's going to have slope f prime of x. In other words, the change in z is going to be f prime of x at that point. And the change in x, well, the slope is going to be change in z over change in x, and you can just write that as f prime of x over 1 in this case. So the direction vector for that guy is going to be, so x is 1. The change in y is 0 because we're fixing y there. And we have f of x at AB. F sub x, the partial of f with respect to x. So that's one vector parallel to our plane, our tangent plane. And then we can do the same thing. We can fix x equals a and look at the, that's going to give us a trace on our surface. And the slope of that guy at our point is going to be f sub y. So this guy is the direction vector for that tangent line. And this guy is going to be the direction vector for this one. So that's going to be 0, 1, f sub y at AB. And I'm going to go through this really quickly because the derivation is not super duper important, but just wanted to explain where this comes from. So we have two vectors parallel to our plane. Remember, to find the equation of a plane, we need a point, which we have. It's the point AB, f of AB. And we need a normal vector. And so to find a normal vector, in this case, we take the cross product of the two parallel vectors. And when we do that, so if we do f sub y cross f sub x, we get the vector partial with respect to x at AB, partial with respect to y at AB, -1 for a normal vector to our plane. All right, so here's our tangent plane. These are the tangent lines to our traces, x equals a, y equals b. We found those slopes, we took the cross product, or we found the directions, took the cross product, and we got this guy is a normal vector. Okay, so putting this all together, so the tangent plane to the graph of f of xy at the point AB, f of AB. So we know we have the point on our plane, AB, f of AB. And we know we just derived the equation, or the normal vector. That's partial with respect to x at AB, partial with respect to y at AB, -1. And so the equation of our plane, putting this together, is partial with respect to x at AB times x minus a plus a partial with respect to y at AB times y minus b minus 1 times z minus f of AB equals 0. But the easier way to remember this is the following. I would remember this formula here. So it's going to be z, bringing the z over, basically, is equal to f of AB, the value of the function at our point, AB, plus the partial with respect to x at AB times x minus a plus the partial with respect to y at AB times y minus b. And that's the formula I would have memorized. So this is kind of nice. Notice this is if you happen to know the equation of the tangent line for to the graph of a function of one variable, it's the same form, right? It's the value of your function, f of AB, just like this was f of a, plus the derivative times, so for a function of one variable, there's only one derivative. So it's just value of the function, f of a, plus the derivative, f prime of a, times x minus a. So in this case, it's the same thing. It's the value of our function, but now we have partial derivatives in two variables. So it's the partial with respect to x times x minus a, plus the partial with respect to y times y minus b. So for example, let's find the equation of the tangent plane to the graph of the function x squared plus 2y squared minus y minus 4 at the point 1, 2, f of 1, 2. Okay, so for the equation of the tangent plane, so we're not explicitly, sometimes you'll be given a point on the plane. You'll be given f of 1, 2 sometimes, but we're not in this case. So we need f of 1, 2. We need, that. We need the partial with respect to x at 1, 2, and we need the partial with respect to y at 1, 2. Okay. So moving quickly, f of 1, 2, plug in x equals 1, y equals 2. We get 1 plus 2 times 4. So 1 plus 8, 9 minus 2 is 7, minus 4 is 3. So when we take the partial with respect to x, not plugging in a point yet. So remember, we treat y as a constant, differentiate with respect to x. What do we get? We just get 2x. And then similarly, well, let me plug in now. X equals 1, y equals 2. And we get 2 in that case. So similarly, the partial with respect to y, treating x as a constant now, differentiating with respect to y, we get 4y minus 1. So then, taking the partial with respect to y and plugging in x equals 1, y equals 2, we get 7. So now we have everything we need. No, that's fine. So we have the equation of our tangent plane is z is equal to the value of our function at 1, 2, plus the partial with respect to x at 1, 2 times x minus 1. So this is partial with respect to x at 1, 2. This is our x minus a. Our a is 1 and our b is 2 in this case. And then plus the partial with respect to y at 1, 2 times y minus 2. So that's a partial with respect to y at 1, 2. And this y minus 2 is, of course, our y minus b. Okay. So going back to the case for functions of one variable. So remember I said the equation of the tangent line in there is, so the tangent line is the best linear approximation of the function at the point A, f of A, or the graph of the function. So we can use that to approximate the value of our function. So y is equal to, if we look at the graph, the y coordinate of a point on the graph is equal to the value of the function at whatever the x coordinate is. So if x is close to A, the y coordinate on the tangent line is going to be close to the y coordinate on the graph of the function. So sorry, we said the equation of the tangent line was y is equal to f of A plus f prime of A, x minus A. And that guy is going to be close to the value of y on the graph of the function for x close to A. So we have, if x is close to A, f of x is approximately equal to the equation of the tangent line, f of A plus f prime of A, x minus A. And we're going to call that guy L of x. The linearization of f at A. And it's going to be a function of x. And so the same thing is going to be true for the tangent plane and the graph of the function. So if we look in the plane, right, we're plugging in points in our in the plane into our function. So there's AB. If we look at some point xy, it's kind of janky here, close to AB, and you look at the points directly above it on the tangent plane and the graph of the function, the z coordinates are going to be close as long as xy is close to AB, because the tangent plane is really, really close to the graph of the function near the point AB. So the z coordinate is going to, on the graph, the z coordinate is going to represent the value of the function. And the z coordinates are close together. So we can say the value of the function so if we're close to AB, the value of the function is going to be approximately equal to the z coordinate on the tangent plane. Well, the way we wrote the tangent plane was we got z by itself. That was intentional. And so it's going to be approximately equal to the right-hand side here. So f of AB plus the partial of f with respect to x at AB, x minus A, plus the partial with respect to y at AB, times y minus B, and we're going to call this guy L of xy. Right, it's a function of x and y. And we can use that to approximate the value of our actual function, as long as the point xy is close to AB. And so this comes directly from the equation of the tangent plane, right? Z equals f of AB plus f sub x, et cetera, et cetera. And so this is how we're going to approximate the value of a function. Pretend you don't have access to a calculator. This is how you would do it. So here's an example of what this often looks like. So yes, let's use this process to approximate the following. So let's approximate 2.92 squared times the square root of 4.08. So not immediately obvious what to do because we're not given a function. We're not given an a and b. So we're going to have to figure that out for ourselves, what we want to be our function and what we want our point AB to be that we're going to be linearizing at. Okay. So basically what we want to do is we want to find, this involves two numbers we're dealing with here, 2.92 and 4.08. So let's just call the first guy X, the second guy Y. So let's say X squared times square root Y. So what we want to do is we want to approximate f of 2.92, 4.08. Right, that's what this is right here, this expression. Okay, so in order to do this, we want to make our lives as easy as possible. So we want to find nice values we want to find a nice value of X that we can plug in and a nice value of Y that we can plug in near 2.92, 4.08. Basically, look for the closest value for X and Y that you can plug in that you know exactly the value of the function. So what's 2.92 close to 3? And 4.08 is close to 4. 3 squared is easy. Square root of 4 is easy. So let's use the point 3.4. Does everyone understand the reasoning there? That's important. So we're going to linearize this function at the point 3.4 because we know the value of the function there and it's easy to deal with. So f of 3, 4 is just going to be 3 squared times square root of 4. 3 squared is 9. Square root of 4 is 2. So that's going to be 18. So the partial of our function with respect to x, so treating y as a constant, differentiating with respect to x, is going to be 2x square root y. And then evaluating that at our point 3, 4, which we're going to need for our equation, we get 2 times 3 times square root of 4. So 6 times 2 is 12. And then our partial with respect to y. So treating x as a constant, differentiating with respect to y, we get x squared. Square root y becomes 1 over 2 root y. So we get x squared over 2 root y. And then evaluating at the point 3, 4, we get 9 over 2 times square root 4. So 9 over 4. Okay. So let's put this together. So our linearization at the point 3, 4 is the value of our function at 3, 4 plus the partial with respect to x times x minus a plus the partial with respect to y times y minus b. So 18 is the value of our function. I'm not going to write that all down. That's fine. Plus the partial with respect to x at 3, 4, which we said was 12. X minus a, which we said is 3. Plus the partial with respect to y at 3, 4, 9 over 4, times y minus b, which is 4. So that's a linearization. So then the thing we wanted to approximate is approximately the linearization at the point 2.92, 4.08. Which is, so plugging in x equals 292, y equals 408. So 18 plus 12 times 2.92 minus 3 plus 9 over 4 times 4.08 minus 4. So if you like, let's write this 9 over 4 as just, so it's 2 1/4, 2.25. And so we get 18 plus 12 times negative 0.08, so negative 0.96 plus 2.25 times 0.08, which we can calculate that. And what we get is 17.24. Is our approximation of this guy. Okay, any questions about that process? I just gave you an expression, and from that we needed to come up with some function. We needed to find a point AB to linearize that function. And then we needed to linearize and then use that to approximate.
On an exam, would we actually have to come up with like 17.24, or could we just leave it in that
This is perfectly acceptable. Yeah, that's perfectly acceptable. As long as it's something you could plug into a calculator and get the right answer, that's fine. No need to simplify further than that. Yeah.
What if the
No,
number
oh,
was
sorry,
like,
the 2.25 was me squeezing that in there. That's 9/4. So if you like wanted to calculate it by hand, that would be, you would do 2.25 times 0.08.
what if the number was like 4.52? What would you round that up to like 5 or?
So it depends on what you're dealing with. So in this case, if it were like 2.92 squared times 4.52, square root of 4.52, I would say round. So that wouldn't be a good example because that's not particularly close. But in that case, I would say round that down to 4, because what you want is we know what square root of 4 is, right? We want a nice round number to deal with in that case. So if you round it up to 5, you would just have square root of 5, and that would be we'd be in the same situation, right? Because we don't know exactly what square root of 5 is off the top of our head. So you want to round down to the nearest thing where you know an exact answer for whatever the piece of the function is. Does that?
We shouldn't expect to see anything like messy like that. It should be.
No. So yeah, that would not be a good example. We're not actually defining what like close is in this sense, but 4.52, you wouldn't get a great approximation in that case. But yeah, it's usually going to be very close, like 4.08 to 4 in this case. Okay, so that was our approximation. So the actual value of our function is rounded to 4 decimals. 17.2225, which is pretty close to our approximation, which is 17.24. So this is actually a pretty good approximation. So in the example you gave, like if we had like square root 4.52, if we use the same approximation at 4, we would not get nearly as close an answer. And that's because so the 0.35 is not close enough in this case to 2.92, 4.52, whatever. But any other questions about that? Okay, so last thing I want to look at is just sort of another, we're going to rearrange our original formula of the tangent plane slightly to get sort of another use out of this. So suppose we don't want to approximate the value of the function. Okay, let's suppose we're here. So suppose we're at a point AB. And suppose we change the X and Y values by a little bit, by delta X and delta Y. So suppose we go from a point AB to A plus delta X, B plus delta Y. So we're at a point AB, we know F at AB. And suppose we change X by a little bit and Y by a little bit. How does our function change? So we don't want to know exactly the value of our function at the new point, which is what we were just doing. We were just approximating the value of a function. We just want to know, how does f change? So approximately how much does f change? Like, what's the difference approximately of f at a plus delta x, b plus delta y, minus f of ab? So the actual change in f is approximately equal to so f at our, let's say our new point is xy. Oops. Oh my God, dude. So we can use our linear approximation to figure this out. So the value of our function at xy, which is close to AB, it's just we're adding delta x to A and delta y to B, is basically take the linearization here, that's f of xy, and then just subtract f of AB. So kill off this first guy. So what we get, so the partial of x with respect to, partial of f with respect to x at AB, x minus a, plus the partial of f with respect to y at AB, y minus b. So I just use xy as shorthand, but x, the new x value is going to be a plus our little bit, delta x, and our new y value is going to be b plus delta y. And so plugging those in, what we get is the partial of f with respect to x at AB. So x, a plus delta x minus a is just delta x. And then doing the same for y. Y, which we said is the new y value, b plus delta y, minus b is just delta y. So if you want to see how f is changing, if you change, if you go from a, b, and you just change the x coordinate by delta x and the y coordinate by delta y, that's going to be the partial with respect to x at AB times the change in x plus the partial with respect to y at AB times the change in y. Which really, this is just a repurposed formula that we already know, the equation of the tangent plane. We're just moving things around. Let's look at a quick example really quickly. So we have the equation for BMI, body mass index. So the body mass index is the weight, W, in kilograms divided by the height in meters squared, W over H squared. So let's estimate the change in BMI. If we go from 40 kilograms, 1.45, height to 41.5 kilograms and 1.47 meters height. Of course, they couldn't give us nice numbers. Lovely. Okay. So I is a function of W and H. So using our formula, so the change, oops, is going to be the partial of I with respect to W at 40, 1.45 times the change in W plus the partial of I with respect to H. Come on. The right of the arrow. Oh, so this is okay. So suppose you're at we want to see how is the BMI changing as we go from weight 40 kilograms, height 1.45 meters to weight 41.5, height 1.47 meters. So this is 41.5, 1.47. So the partial of I with respect to H at our initial point, so 41.45 times the change in height. And we can calculate this out. So our change in, just so we know what's going on here. What's our change in weight? What's our delta W? It's positive 1.5, right? We've gone from 40 to 1.5, so we've increased by 1.5. And our delta H, we've gone from 1.45 to 1.47, so that's positive 0.02. And then, of course, our partial with respect to W is going to be 1 over H squared. And our partial with respect to H is going to be negative W over, negative 2W over H cubed. And then so on and so forth. You would just plug in H equals 40, or W equals 40, H equals 1.45 to figure this out. And they're not super nice values, but that is how we would do that. But the point is, what we're doing is we're looking at how a function is changing. We're approximating it. We don't need to know the value of the function. We just want to see how it changes as we go from this point to this guy here. And we use this formula here. Okay, any questions about anything from today? So the answer is about 0.2 when you plug in everything at the end. But that's in the book. Okay, if not, that's it for today. I will see you guys on Wednesday, and then I will go over to the office hours meeting until 1 o'clock. All right. Have a good one, guys.